Hey guys, welcome back to Couch Potato Structural Analysis course. In the previous session, we have seen what is static determinacy and how do you determine static determinacy and what are the types and how are they classified as external static determinacy or internal static determinacy. In today's session, we will see how kinematic determinacy is determined or what is called as degree of freedom. So we have got here some standard supports and we'll see how to determine and what do you mean by degree of freedom. So we have got a fixed support here. So for this fixed support, it cannot move in any direction. Let us say it is X or Y, or it cannot even rotate. So degree of freedom for fixed support is equals to 0. Next we have a hinge support. Hinge support, the degree of freedom is 1. How? It can rotate. There's a moment here. So it has a degree of freedom of 1. Now we have a roller support. Roller support can move in this direction, that is delta x. Let us say it can also even rotate at theta. So the degree of freedom for this roller support is 2. For a free support, it can move in either delta x direction, delta y direction, or even it can rotate in delta x, theta x, I'm sorry. So degree of freedom for free support is equals to 3. So now we have vertical shear support, which is a hinge shear support. This can only go in delta x direction, delta y direction, sorry. So degree of freedom for this is nothing but 1. Horizontal shears of hinge can move in only one direction, that is delta x. Degree of freedom for this is 1. For a rigid joint, when such a arrangement is made in this fashion, it can rotate in theta. It can also have a delta x direction, it can have a delta y. So a small displacement towards delta x, small displacement towards delta y. It can also rotate in this fashion. For this, the degree of freedom will be 3. Now, so for internal hinge, what are the different possibilities of directions? So we have this here, rotation in this direction, rotation along this direction, can even go like this, delta x, this is delta y. So degree of freedom for internal hinge is equals to 4. For horizontal shear joint, we have direction of this particular thing moving here, that is delta x, right? We can have this direction because for this one it is also delta x. It can also go up and down because it's a shear joint. It is delta y. You can also have a degree of rotation. So total number of degree of freedom is equals to 4. 1 theta, 1 delta x, another delta x, and one more delta y. Now moving on to internal hinge. Internal hinge for frames, which is having a different arrangement shown in this figure. So for this, it can have a 3 types of rotation here. It can either go in this fashion, or in this fashion, or in this fashion. So there are 3 thetas. It can have a small displacements towards x, small displacement towards y. So degree of freedom for this is equals to 5. 1, 2, 3, 4, 5. Similarly, for vertical shear, we can have delta x in this direction for this. For this, we have delta y in this direction, and then we can have a small delta x towards that direction, and also we can have a theta. So now we have degree of freedom for this one is equals to 4. So these are the standard cases for which we have seen the degree of freedom and how to evaluate the degree of freedom. So moving on to important notes and points. So for, let us say, if we have a truss. So in that pin jointed plane frame, it means pin jointed plane frame. This is essentially meaning truss. degree of freedom from each joint will be 2, because it's a plane frame we generally use in problems in structural analysis. We generally take number of joints into 2 for each joint. Please remember, this is for each joint. So similarly for space frames it is 3, for rigid plane for each joint it is 3, and for rigid space frame it is 6. Why? Because it can have a delta x delta y direction, it can have delta x delta y and delta z direction, okay, similarly and so on. Important points to note down here are, if roller support is provided in the pin joint truss, dk of that is equals to 1, that is delta x only. If you remember or recollect, we have seen that roller joint is this, okay. We have said that degree of freedom for this is theta, and also it has ability to move in delta x direction. But why don't we have this moment? Since trusses are not subjected to moments, we assume that theta equals to 0. So if hinge support is provided at the pin joint truss, the dk or degree of freedom is equals to 0. For hinge support, there was 1 degree of freedom, which was theta. Okay, now because theta is equals to 0, degree of freedom equals to 0. Sorry, it's important points, so I have to remember. Moving on, we'll solve some problems. Okay, so in the first example, it is saying what is the degree of freedom of this particular hypothetical structure. So how do you determine that? So this is a fixed structure here. So for degree of freedom for this equals to 0, because it cannot do anything, it cannot have an axis of rotation or any displacement. For this we have seen internal hinge, we have seen it is 4. For hinge support it is 1. For horizontal shear joint it is 4. For roller support it is 2, and for vertical shear joint hinge support it is 1. And if we say this is completed, no, it is not completed, because the free end is still there. For this the degree of freedom is 3. So adding degree of freedom, we have 0 plus 4 plus 1 plus 4 plus 2 plus 1 plus 3. This comes out to be 15. Okay, now we'll go to another example. This is a different type of example. Remember, if you remember this first point in a previous slide, we have seen that for each joint the degree of freedom for each joint it is 2. So number of joint here is actually 1 2 3 4 5 6 7 8 9 10, or you can just name them 1 2 3 4 5. For each of these joints it is degree of freedom is 2. If you remember, for roller support we have seen that degree of freedom was 2, but for trusses it will become 1. And similarly for hinge support, in trusses the degree of freedom will become 0. So we have degree of freedom is nothing but 2 into 1 2 3 4 5 9 plus 1, that is degree of freedom is 19. Moving on, we will see what is kinematic determinacy of the structure for third example. It is a rigid joint frame. Okay, so for this the degree of freedom for a fixed joint is 0. So similarly for this and this it will become 0, right? And next, for each of these rigid joint we have seen it, a degree of freedom will be 3. So 1 3 3 3 3 and 3, that is 6 times 3, the degree of freedom is equals to 18. So this concludes what is degree of freedom, how to determine them, and how do you use the knowledge of degree of freedom in structural analysis. Now moving on to what is called a stability analysis, we will see how structures can become unstable, or when one of the special conditions the structures can become unstable. So we have here stability analysis. In this we will cover 4 points with examples, and when you can say a structure is stable or when you think it will become unstable, we will calculate how to do about it. So first point says the structure must be stable both internally and externally, or at least it should be supported by some other means. So what do you mean by this? Let's take this example. It is a pin jointed truss. We'll calculate the degree of static determinacy. So degree of external static determinacy will be, for this it is, so number of unknowns are 4. For A, B, we have AX, A by, BX, BY, and number of equilibrium equations are always 3. So degree of external static determinacy is 1. For degree of internal static determinacy, we have the formula m minus 2j minus 3. Number of members are 1, 2, 3, 4, 5, and 6. So number of members are 6 and number of joints are 1, 2, 3, 4, and 5. So number of members are 6 minus 5 joints minus 3. This is coming out to be minus 1. But total static determinacy is 1 minus 1, that is 0. So structure is stable globally, but it is unstable internally. Structure cannot be unstable internally. That is what the first point is. So the structure is internally unstable, or there is an excess redundant force. That is what the first point is. Moving on to the second point, he says structure must be stable not only globally but also locally. So we'll calculate what is the static determinacy of the structure. So external static determinacy is simple. 3 unknown reactions are there. We have 3 equilibrium equations. External static determinacy DSE is equals to 0. And calculating TSI is m minus 2j minus 3. So number of members is 1, 2, 3, 4, 5, 6, 7, 8, and 9. And number of joints are 1, 2, 3, 4, 5, 6. So number of joints, number of members 9 minus 2 into number of joints is 6 minus 3. This is also 0. Total determinacy is equals to 0, because 0 plus 0 is 0. This truss will get crushed by these two forces, P1 and P2. But it is globally stable. At the first sight you will say, yeah, it is easily, you can determine what are the different forces acting on it, and which member is under tension, which member is under compression. But this cannot be stable structure. It will get crushed. So we have a special loading condition here. If you say that forces are parallel, suppose these are the parallel forces P1 and P2, and also the reactions are parallel to the forces, because of this the structure can be stable. But let us say if we apply a force in the x direction, this starts moving. This is not a structure anymore, it's a mechanism. Okay, so under some loading condition it will become unstable. So this structure is actually unstable. Sorry. Also, when the reaction forces are concurrent, like I've seen here, the reaction is converging to a point. Suppose this point is A. Because of this reaction are concurrent, the forces, the structure is also unstable. So it should be either parallel or concurrent, converging to a point. Now, that is the third point. That is the third point. So now if you move on, if the reactions of a beam on one side and are coinciding, the structure is likely to collapse under some loading condition. So if we observe here, this is the beam. The reaction forces are converging this point to this point. So under these conditions also, the structure will become unstable. So now we have seen when the structures can become unstable, or when the structures are said to be indeterminate or kinematically determinate or indeterminate. Now we have laid the foundation for determinacy of a structure, very basics of structural analysis. So in the next session, we'll see how to determine forces in a truss, plain truss. What are the different methods used for that? Okay, stay tuned. Thank you. Bye bye.